go from this slide. Okay. And remind me of your name.
William.
Okay. William Shamoon?
Yes, sir.
Something like that. Okay. And
Connor Bailey.
Connor Bailey, got it. And remind me of your name. Sorry.
Patrick Williams.
Patrick. Okay. Anyone else coming since the cover? Okay. Okay, all Y chromosomes, where are the X's? Story of my life. Okay, never mind. Okay. There you go. All right, good deal. Thank you. And remind me of your name, please. Corey. Corbin. Corbin. I got it. Okay. Anyone else coming since the call? Okay. All right. Did I sort of gather from what let me even turn on the projector for you today. I'll feel magnanimous. Okay. Any questions from anything someone asked earlier? Any questions from anything we covered before?
Yeah, homework I was trying to see,
21? Okay. Something to mark my place. This will be on page. Thank you. Appreciate it. This is on page 450?
Yes.
Okay. All right. Page 450. This is 7.1 exercise. Number 21, you said, right?
Yes.
All right. It says find the area of a region. It says first sketch the region bounded by the graphs of the equation, and then find the area. 21. All right. And remind me of your name. Second, Preston? Okay, got it. Deal. Anyone else coming since the call roll? Okay. And remind me of your name?
Davis.
Davis, got it. Okay. Now, here are the two functions, x squared plus 2. Alpha of x is equal to x squared plus 2. And what color would you like g of x to be? Say again?
Red.
Red, okay. It's really sort of an orangey red, but the other one I was afraid if I hit that it would end the recording. So g of x is x plus 2. Okay, now, I think I'll go back to the dark color to start with.
It's x to the 5th plus 2.
Oh, you're right, that's x to the 5th plus 2. Okay, I can't read. That makes for an interesting problem. Okay, let's plot out some x's and y's here. Won't need that many, I'm pretty sure, but I'll just plot them out there. Okay. X to the 5th plus 2 is a pretty interesting function. When x is equal to 0, where are we? 2. X equal to 1, we would be at 3. X equal to negative 1, we'd be at 1. And if you go to x equal 2, you're way off scale, okay? So it's a function that looks somewhat like this. yuck, get out of there. Okay. It's probably not that distinct, but something kind of like that. Okay? And g of x is equal x plus 2. And let me get my G color back. Here we go. At 0, it's 2. At 1, it's 3. And at 2, it's 4, and blah, blah, blah. And at minus 1, it's 3. Okay. Interesting. Something like that, if I drew it correctly, which is language.
Bailey.
Huh?
Bailey. That's my name.
Yeah, I couldn't hear.
Bailey.
Bailey?
Yeah.
Okay, got it. My hearing's so bad.
No, you're good.
Okay. All right, anyone else coming? This is called wrong. Okay. Now, my drawing kind of stinks, but I hope you know that this one is symmetric about the this point, and this one's symmetric about that point. So they didn't give an interval on here. They said sketch the region bounded by the graphs of the equations and find the area of the region. Well, there's two areas here, right? Down here you don't have anything bounded. Up here you don't have anything bounded. You have two right here, but this one, the L function is greater than G, and up here G is greater than L, and those two lobes are supposed to be the same. My drawing isn't. So what would be your guess right off the top? Say again? Well, for the area, that's what I was asking for. Okay. In other words, F minus G would be here. Here it's G minus F. In other words, F minus G would be exactly the opposite of it. So the sum of these two would be 0.
Oh.
Is that what the answer was?
Yes.
Okay. And that's probably what 3, right?
Yeah.
But let's actually do it. Now, if you really wanted to know the total area, irrespective of who's on top, okay, then you could just do either one of them and double it. But I bet you the way they do it, well, I don't know. I don't know how they do it. Sketch the region and find the area of the region. And I was just guessing they're going to say 0. Did they? Is that indeed what they have in the back?
They have 2/3 in the back.
Oh, it's not 0.
It's not 0.
Okay. Okay. Well, then what they're saying is then do the total area of either one and double it. So I'm guessing that, okay. Which, if you're only looking for area, you don't care who's on top. But I was not sure which way they were defining this problem. So let's do it. So you want to take the, do you agree that they've got to be symmetric?
Yeah.
Okay. So let's just do one side or the other. Would you rather go 0 to 1 or negative 1 to 0?
0 to 1.
0 to 1 sounds good to me. Who's on top 0 to 1? G. Okay. So we're going to do our, I think I'll go back to the dark color here, and we'll do little strips like this. Okay. So therefore we're doing dx's. I guess you could have done dy's, but everything's in terms of x's. Let's go with dx's. So there's your dx, is the thickness of that strip. What's the length of that strip? Now the length of the strip is top minus bottom, right? And what's the top of that strip? The top of the strip is which function? The g function minus the F function, right? So the length would be that, okay? So that would be x plus 2 minus x to the 5th minus 2. Would you agree with that?
So it would be plus 2.
Well, okay. there it would be plus 2, okay? And then when you move the parentheses, it's minus 2, okay? So yeah, that's probably more correct to do it that way. So now we're doing the integral from 0 to 1, right? So the integral is from x equals 0 to x equals 1 of this thing here, and I want to do my scratch work here. X plus 2 minus x to the 5th minus 2. Agree with that? Okay. What do you notice there? The 2 plus 2, 2 minus 2 goes to 0, and that just gives you the integral of x minus x to the 5th. That's your height, and then your width is dx, and you're summing all those from here to there, and that's your integral. 1 from 0 to 1. Does that make sense? Okay. What's the antiderivative of x? X squared over 2 minus x sixth over 6. Evaluate that between 0 and 1. I'll do the 0 part, y'all do the 1 part. What's the 1? What do you get when you plug 1 in? Say again? Okay, that would be 1/2 minus 1/6, right? And now I'll do the 0 part, 0 minus 0. I've done it. Okay, good. Okay, so this will be 3/6 minus 1/6 is 2/6, which is 1/3. And then just double that, because by symmetry, you see this hump and that hump are the same distance there. Now, you don't have to do it that way. You could do this part from -1 to 0, but then you have to do x to the 5th plus 2 minus x plus 2. So then it would be x to the 5th minus x. When you do this one on top and that one on bottom, dx, and then do another integral from 0 to 1, the one we just did, and you'll find out they do turn out the same. Looking at it, and not my picture, but you know, a real good graph, you would see those have to be symmetric, so you can just do half of it.
So the integral would be -1 to 0 on top?
Okay, yeah, if you do -1 to 0, then you would do this minus that.
Yeah.
Right. Okay. You want to do that one?
No, I'm talking about the actual integral.
The what?
It'd be -1 to 0 on top.
Yeah, -1 on the bottom, 0 on top. Yeah, for that second. Because you always go left to right. Anytime you reverse those, then you reverse the, you negate what's inside. Yeah. Okay. And that gives you 1/3, double it, and it's 2/3. Did that answer what you needed?
Yeah.
Okay, good deal. Any others? Glad y'all are working these. Good deal. Okay, I want to go back to where we left off. I think that was example 3. So if no one needs this anymore, I'll erase it. Okay? Okay, they don't have example 3 on the slideshows, so let's do that. The sine and the cosine curves intersect infinitely many times. Goodness gracious. Bounding the regions of equal areas as shown in figure 7.7. Hopefully enough of you have books you can see that. If you don't, I'm not going to try to draw it. Goodness, I got something in my eye. Okay. Oh, okay. It's a heavy book. Here is the sine function, the dark colored graph. Okay, here's the cosine function, the lighter one. And you have this region and that region and this region and that region. And they're saying each of those is the same area, and they sure look like it. Yeah, they look like they'd be exactly the same area, even though they're sort of mirror images of each other, but they're perfect mirror images. So basically it's saying just go take one of them. Well, let's see what it says. Bounding regions of equal areas is shown in this figure. So let g of x equal cosine x, f of x equals sine x. I might have to get the figure up there again, but let me do this. This is example 3 in the text. Find the area of one of these regions. Okay? I guess I need to do, I don't want to hold the thing up there, so I'm going to try my best to draw this region. Okay? The sine function goes up like this. This goes to 1. We'll do pi halves here and pi there. Okay, sine goes like this, and 3 halves pi and 2 pi, and down to -1 and up to 0. Whereas cosine starts here at 1 and goes down to 0, down to -1, and up to 3 halves pi. Okay. Now we're going to repeat this area over and over again. So it says find the area of one of those regions. So let's choose this one. Now, of course, we have to determine what value for x and does anyone know where these two intersect? The sine is equal to cosine. Pi fourths, exactly. Sine of pi fourths equals. So, anyone want to hazard a guess about what this one would be? 5 pi fourths, just past 4/4 pi. 5, that'd be 6, so that'd be 5 pi. Okay, so this will be going from 5 pi fourths, and this is going pi fourths. Okay, so from pi fourths to 5 pi fourths. Now, short of that, what you could do was do sine x equal cosine x and see what that works out. And I think the best thing to do there was we divide and get tangent x equal 1 and see where that's at. And sure enough, you'll find those are the two values that make that true. So there's several ways to get there. One graphically, which was what we did, but you could also do it analytically. And how did that show up? Okay. So what would be how can we determine the area of that region? On the one we drew, who's on top? And I made an assumption in the last class. I taught Cal 1 this morning, earlier this morning. And unfortunately, I found hardly anyone who knew any trig at all, which was a little scary. Hopefully some of you had better know some trig, since I was supposed to be your instructor in that, so you better know. Who's on top here? Which of these functions is on top? Maybe I should have used different colors. Sine's on top. And is that what they say? They do it the other way. They say let g of x equal cosine x, and that's the one on the bottom, which I'm okay with, and f of x equal sine x. Okay? And then you do any arbitrary little. Okay, let's back up. Do you think you want to do dy's here? Please say no. Okay, yeah, absolutely not. Here you're going from sine to sine, from cosine to sine, down here cosine to cosine. You don't want to do that. Let's do it this way, and always the sine on top, cosine on bottom. Yes, that's the way to go. So, what's your area of that little rectangle I drew? What's the thickness of it? dx. And what's the length of it? The length is sine x minus cosine x. And then the integral will be the total area from pi fourths to 5 pi fourths, and your thickness is dx. Now, I don't know if you like to put parentheses in there or not. You can. It actually probably is a little better so you don't for some reason think this is by itself and it's only cosine x we get out of. Anyway, what would you do next? You set up the problem, which a lot of times this is the toughest part, is graphing it, setting it up, and then usually the calculus is the easy part, right? Okay, so let's go. What's the antiderivative of sine x? Okay. Sounded like there was a lot of question there. Does everybody agree with that? Second? Is what? Negative cosine, okay. Minus a cosine x. What's the antiderivative of minus cosine x? Second? A minus sine x, okay. And that's going from pi fourths to 5 pi. I can't. My pen is so slow. Fourths. Okay. All right. Now, the minus of cosine of 5 pi over 4 minus the sine of 5 pi over 4 minus a minus, which is plus the cosine of pi fourths, and minus a minus, which is plus the sine of pi fourths. Should have planned ahead, right? Not run out of room. All right, now we got to figure out what the cosine of negative pi fourths is. Well, where are we, Waldo? This is the first quadrant, second quadrant, third quadrant, fourth quadrant, right? So where are we with this one? Second? Which quadrant are we at? Third quadrant. And what's the SIGN sign of the cosine in the third quadrant? Negative. Okay? So minus, okay, and what is the actual value of cosine 5 quarters pi? Second? Root 2 over 2. All your quarter pies are that value for sines and cosine, and it's a minus, sine's a minus, so this will be a root 2 over 2. And the sine, what's the SIGN of the sine in the third quadrant? Second? Negative also, and negative negative would be another plus root 2 over 2. Remember, they're the same. Okay? And how about the SIGN of, where are we in pi fourths? First quadrant, and what's the signs there? SIGN sign. Everything's positive in the first quadrant, so that's going to be another plus root 2 over 2, plus another root 2 over 2. And that looks a lot like 4 root 2's over 2, but 4 over 2 would be, wouldn't that be 2 root 2? All right. Everybody agree? All right, let's see what they got. Oh, look at that. They got it right. Good for them. See how that works? Okay. All right. That's example 3. Now, I can't remember if last time, if my memory right, our system wasn't working at all. Okay, so I still was recording, but I couldn't get it uploaded till sometime the next day or something. But it's out there now. And by the way, let me time out. Okay, since more people are here, I was starting to say this early on, but so few people are in here. I did get, believe it or not, your syllabus updated, and I put that out on Blackboard under my syllabus, or our syllabus, or whatever it calls it, on the blue tabs on the side. And then I actually moved some things around. I think I moved my locator card to something about instructors' schedule or all, something like that. So I have another tab, I put that under. And then under the course handouts and more, strange title, that's where I put the research paper instructions and all the PowerPoints that we could possibly do this term, which is way more than we're going to get to do, because we can't do every section and every chapter. We're going to hit the majority. Okay, so I put those out there, and then I put some of the websites that either I found or students have found and said they found useful in the course. So they're out there. Now, some of those websites, I've got to go and check on these. They may be the old book that we use, because some of them are book specific. And I didn't have a chance. I didn't even have the stuff with me to give it the new one. So I may have to do some modifications there, so that some of them may be useful, some not. But you'll just have to see. But and then the YouTube link is out there too. So you can go to, what do I call it? Course handouts and more. When you go to that, there's where the vast majority. One of them's at my syllabus or our syllabus or something like that, and one of them's at instructor schedule or whatever. Okay. But most of the bulk of the course material is under this one. So, did want to point this out to you. And this next example, example 4, even though it's not on the slide set, notice here, clarssoncalculus.com for an interactive version of this type of an example. Now this is interesting that they put this on one they didn't even show on the PowerPoints. So you've run into now 3 websites that this author provides for free. Okay, one of them is the calcchat.com, where all the odd number exercises are worked out. The other is calcview.com, where selected odd numbers are given more detail. And now we have a third one where some of the examples are expanded on. Okay, interactive versions of this. Example 4 is one of these. And that probably would have helped on that homework exercise that you had questions about. I didn't realize that at the time. Sorry, I've got to sneeze. Y'all awake? Okay. Good deal. So let's do example 3. All right. Let me clear. Oh, I forgot to mark Justin. Yeah, example 4. Sorry. Let me mark Justin here. Does anyone else come in since I called roll? Okay. All right. Find the area of the region between the graphs of f of x is equal to 3x cubed minus x squared minus 10x. Okay? What color you want g of x? Blue? Okay. Second? Which one?
No.
Not that one?
No, that's fine.
That's fine, okay. I thought he said Carolina blue, and I thought, does somebody know what Carolina blue is? G of x is equal to minus x squared plus 2x. Okay. Now, so find the area of the region between those graphs. And they say begin by setting those equal to solve for x. I'd say begin by graphing the equations. It doesn't really matter which you do. But let's do what he suggested first. I think there's a reason for that. Later, it might be harder to graph, or you might have to use graphing utility or something, and then you might still have to figure out what those points are. But do the graphing first, you're going to see the points, obviously. So let's go on and do them. So where do these two intersect? Well, what we do is set them equal to each other and see where they intersect. Well, that's not what I wanted to do. Yuck. I'll go back to dark. Okay. So set f of x equal g of x. So 3x cubed minus x squared minus 10x is equal to minus x squared plus 2x. Now, how do you determine where they're equal? I mean, we set them equal to each other. Where do you proceed from? How do you proceed from here? Okay, move one side to the other. I suggest let's add x squared to both sides. You okay with that? And subtract 2x from both sides. And what does that give you on the left? 3x cubed. Second, minus 12x is equal to 0. And what would you suggest we do next? Factor. And what do you get? 3x times x squared minus what? 4. Are you through factoring? Why not? So 3x times x plus 2 times x minus 2. So 3 points of intersection are what? X equals 0. I can't hear. Okay. X equal negative 2 and x equal positive 2. Okay. Now, when I draw my graph, you'll see exactly that those three are there. I have to stop and pause here because I need to see how big to scale it. Got to have a pretty big Y scale, fairly small X scale. So this is not going to be, just like the books, not going to be to scale. Okay, there's 1, 2. There's 0, of course. 1, 2. Positive. And going, we've got to go at least to negative 8. So let's make that a negative 8. This a negative 4. This a 2. There's a 6. There's a 1. 3. 5 negatives, by the way, and negative 7, and then on the positive side, let's go up to, I don't need to go up to 8, they only, well, I've got it about the same, so I'll do an 8 up here, a 4 here, a 2 there, a 6 here, a 7 here, 5 here, 3 here, 1. Okay? So, plugging in x equal negative 2, that would be negative 8 times 3 is negative 24, minus another 4 is minus 28, and then plus 20, so that's your negative 8 down here. And 0, 0 is going to be there. 1 will be pretty easy. Let's do that one. That would be 3 minus 1 is 2, negative 1. Wait a minute. It would be a negative 3, minus 2 is minus 6, plus 10, so it goes up to plus 4. No, I'm not doing something right. Negative 1. So negative 3 minus 1 is negative 4. Plus 10 is positive 6. I said it right, but did it wrong. Okay. And then at positive 1, this would be 3 minus 1 is 2. Minus 10 is minus 8 again. Yep. And 2 will be 0. Let's just see that. 24 minus 4 would be 20 minus 20. Yeah, plus, yeah. Okay. So there's our F function. It's supposed to be fairly smooth. I did it a little too pointed. Here's the G function. I'm going to cheat and just do, I know that point's the same, this point's the same, and this point's the same, so it's going to be something like that. Probably not that humped. At 1, G is 1. So yeah, not nearly that humped. Okay. But it really doesn't matter, just a general collection. Okay, something like that. So, if we're finding the area between those two curves, again, and this is, oh, yuck. This is our f of x, and I forgot to change colors. That's why I put colors to begin with. Wrong color. That's the Carolina blue. Okay. This is my g function here. G of x. Okay. Okay. And what you have to do here, don't make the assumption these are symmetric. They're not. Okay, so you actually have to do f minus g for this part from minus 2 to 0, and g minus f for this part from 0 to 2. So you have two different integrals you have to do, and I have very little room to do them. So is it all right if I erase this part over here? Okay. That was necessary, but we've already got it figured, so this takes forever to erase. Let's leave our picture there and go from there. All right, so you tell me the first, let me get my color back. My first integral. This one will be from -2 to 0. What's the integral there? Yeah, I'm going to do it off to the side so I'll take less room. 3x cubed minus x squared minus 10x. That's the f function. That's on top. Minus the g function, which would be what? Can we go on and negate it? Make that plus x squared minus 2x. Combine like terms. X's go out, and you have 3x cubed minus 12x. All right? Okay? So 3x cubed minus 12x. Oh, probably should have done this too. There's my dx, and you got f minus g. There's the length. See it? So there's your length, f minus g times dx. Okay? You tell me the antiderivative of 3x cubed. Ding, 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 ding. 3 over 4 x to the 4th. Okay, I couldn't tell if you said it or not. Okay, antiderivative of minus 12x squared. I mean minus 12x.
6x squared.
Second?
6x squared.
6x squared. Okay, evaluated from -2 to 0. The pen is really, really slow. I'll do the 0 part. Done. Okay, you do the -2 part. Second? Okay. Yeah. X to the -2 to the 4th would be a positive 16, and 4 will go into that. 4 times 3 is 12. So that would be 12. If it'll write, there it comes. Okay. Minus. Now wait a minute. That's supposed to be a minus in front because this is the second part. The 0 part's first. This is the minus. So this then will be a plus, And what would that be? Again?
Negative 24.
Minus a minus 24, right? Watch these signs, folks. This is the worst part of these problems. Okay. Worst part is that thing. Okay. The 0 part was the first part, and that was 0. So it's a minus this, evaluated at minus 2, and evaluated at minus 2, this is a 12, but it's a minus 12. And it's a minus, which is a plus, and this evaluated at minus 2 is a positive 24. Right? Okay. You see why the minus signs?
Because there was a negative sign at the beginning of the even.
Okay.
Because it was 0 minus.
Yeah. The positive part here is the 0. That's 0 times 0. Okay. And then minus this part, which would be a plus and a minus. Okay. Okay. And that's in parentheses, minus and plus. So the minus sign reverses both signs. Because the negative 2 is raised to even power, so it becomes positive everywhere. So this just comes out to be 12. So this half of it is 12. Okay? And by the way, if you ever get a negative area, think again. You can't have negative areas. You either reversed you did something wrong. Okay? You either have the wrong function on top and the wrong one on bottom, or whatever. You did something incorrectly, okay, if you come up with a negative area. So go back and review that. All right, the second part, the g's on top. So this is going to be plus the interval from where to where? 0 to 2. And our little strips are going to be something like this, where now your length of that strip is what? The length of the strip is g minus l. So that would be a minus x squared plus 2x. I'm going to run out of room really rapidly here. Minus this one, so that's going to be a minus 3x cubed plus x squared plus 10x. And your thickness of that is dx. Okay? Now when you do that work, I think I'll come over here and do it. Integral from 0 to 2. Here you have a minus x squared and a plus x squared. Those go to 0. Plus 2x and a plus 10x. That's going to be 12x. And here is a minus 3x cubed. Which, by the way, is exactly the opposite of this one, because you would, yeah, this minus this, that minus, they're the opposite of each other. So you could have just looked like this, and reversed it for that. That would be fine. Now we need to do the integration, and what would that be? Antiderivative, same as we had before, but reverse order. That would be 6x squared minus 3/4 x to the 4th. Right? Evaluated from 0 to 2. This thing is just taking forever. Okay. Well, let's evaluate those. Actually, it's the same values, isn't it? It's going to be a 24 when you plug in a 2, okay, minus 12. Perfect. So that's going to be 12. So even though they don't look like it, they certainly weren't symmetric to each other. They don't look like they could possibly have the same area, do they? Yes, yeah. They could. This only went up to 6, that went down to 8. Yeah, it's possible, and in fact, we see it is true. So the total area we get is 24. Okay, let's see what they got. Oh, did they get an answer? There it is, yeah. They got 24. Okay. And if you look at the one in the book closely, you can see how they could be the same area. It wouldn't be obvious they were, but they certainly, the math comes out the same. All right. Now, I hope they have example 5, do they? Let's clear, well, let's just go through. Any question on that before we move it? Okay. No. I was afraid of that. All right. Let's clear all the ink. It kind of gets me, and this not just this author, it seems like most of them. They will put on the PowerPoint the very easiest of the problems, and then the ones that are a lot more difficult they don't have, so making me draw. So example 5. Find the area of the region bounded by graphs of, this time, x equal 3 minus x squared, not y squared. Can't have. Okay. And what do you want the second one to be? What color? Green. Okay. And this will be x equal y plus 1. Okay. So here are 2 graphs. Here are 2 curves. One's a line. But what is different about this is that it's x is a function of y, not y is a function of x. Okay? So that's not a very horizontal line, is it? I must be thinking negative thoughts now or something. I'm going downhill. And I think I'll do the easy one first. X equal y plus 1. Well, this has a x-intercept of plus 1, okay, and a slope of 1. So it's a line that does something like that. That's not a very straight line, but you get the general idea. Okay? The y function, the other function, the dark function, is a sideways parabola now. So when y is equal to 0, x is equal to 3. Okay? When y is equal to 1, x is equal to plus or minus 2. I'm sorry. When y is equal to 1, x is plus or minus 1. No. Yeah, plus or minus 1. Okay? And when y is equal to 2 plus or minus 2, this is a minus 1. So somewhere back here is a minus 1. So here, okay. So this is approximately, whoa, yeah, the curve, okay? Yeah. And so we're doing this. Now, question for you. You think dx's would be the way to go here? No. dy's much better. Okay? So, let's do strips that are basically like this. Oops. Like this. Okay. Let me clean that up some. Oh, man. Here is your strip. Your dy is now the thickness. what is your length of that strip? Dark minus green, right? We don't have function names for them, so it would be the dark one minus the green one. That's the length. Farther positive to less positive, or positive to negative, whichever it goes. So what's your integral? From where to where? What's this point down here? Oh, you're doing dy's, so where are your y's going from? I guess I should have labeled my points better. This point here is, the x is minus 1, the y is minus 2. Okay? This point up here is x equal 3, y is equal to 0. Okay. That covers our extremes. But we're doing dy's, oh no, extreme in y. This one up here is 2, 1. Right? Yes?
Right minus left is left minus right.
Right minus left. This one minus this one. It's always the more positive minus the less positive. Positive minus negative. Or more less negative minus more negative. Always greater minus less. Now, perhaps we should have gone back. This was a really good problem to actually to calculate the point of intersection. So let's do that. 3 minus y squared is equal to y plus 1. Now what I would do is add y squared to both sides and subtract 3. So add y squared and subtract 3. So this gives me a 0 on the left, and that's equal to y squared plus y minus 2. And what's your points of intersection? Second? Yeah, y plus 2, y minus 1. So y is equal to negative 2. That's that one. And y is equal to plus 1. Okay, and that's that one. But plug those back in here. When y is equal to negative 2, this will be 3 minus 2, which would be a minus 1. So your x is minus 3 minus 4, which is minus 1. So x is equal to minus 1. That's where this comes from. And plugging the plus 1 up here, x is equal to 2. So that's where that one comes from. So what are your limits on y? From minus 2 to plus 1. So that's going to be your integration limits. Minus 2 to plus 1. Okay. Let me get some of this out of the way because it's gotten really... The eraser didn't pick up. There we go. Okay. Get this out of the way too. Okay. All right. And what's your integrand here? What's that difference? The dark minus the green. That would be 3 minus y squared minus y minus 1. Well, that would be 2 minus y squared minus y. It doesn't matter how you write these. That's just as good as any. So let's do that as your integrand. 2 minus y squared minus y. And your differentiation is with respect to y, which is good because that's what you're in terms of. And y going from negative 2, the y is going to plus 1. Everything's in y. What's the integral? Antiderivative. Say again? Except it's not x. 2y minus over 3 minus y squared over 2. Okay? And that's evaluated from y equal negative 2 to 1. So let's do the 1 first. What does that give you? Plug y equal 1. A little louder. 2 minus 1/3 minus 1/2. Okay. And then minus 2 times a minus 2 is plus 4. Okay. Minus a minus, which would be plus, and 2 or negative 2 to the cubed would be, so that, but it'd be a negative, so that'd be minus an 8 thirds. So let me go back and change again. Again, these pluses and minuses will eat you alive. Okay, 8 thirds. Okay, and then you have a minus, which is a plus. But this time, it doesn't change sign because it's an even power, and that would be what? 2. Plus 2. Turns out being plus 2, right? All right, then let's combine what we know. The pluses add up to be 8, right? 4 and 2 and 6, 2 is 8. And the minuses are, yuck, we got to get them to 6. This will be 2, 6, 3, 6, and 16, 6. 16 and 3 is 19, and 2 more, 21, 6. Minus 21, 6. Someone check my math, because I tend to, when I go too fast, make a lot of errors. Is that right? Okay. I don't know if you want to make that 48, 6. No, you don't want to do that. Let's get this to 7 halves. Okay. And then you can do 16 halves minus 7 halves is 9 halves. All right. Let's see if that's what they get. Oh, good for them. They got it right. See how to do that. Now that one's pretty gory detail. Nothing symmetric, nothing do, so it's probably a great idea rather than count on your drawing, and certainly when counting on my drawing, to figure out what those endpoints are. And by setting those equal to each other, we got that y is equal to negative 2 and y is equal to plus 1. Plug in those values into these two to get what the x values are. And that would be a negative 1, negative 2, and a plus 2, plus 1. So do those, and then determine which is the greater and the lesser. So it's the greater minus the lesser, and do your integration from there. Watch those signs, because you have a function with changing signs. You are going from 2 different values here, okay? The first one are these signs minus the second one with the opposite signs, but you got a number that changes the odds, not the even, so it's real easy to screw up the signs. And if you ever get an area that's negative, check to see first if you did the difference right, and then if you did, make sure you didn't make an error in your signs. Okay. They actually, I think, try to do the problem with dx's. Oh, why would they do that? Number one, you wind up with integrals that really stink. And here you have to do 2 integrals. You have to do y as a function of x here, which would be a positive value. Y is equal to a function of x here, which would be a negative value. those two, it's really miserable. Here you just have one, the upper minus lower. Still, you got a radical form down there, which taking those derivatives or integrals are not pleasant at all. Okay. Do you want to see it done that way? Please not. Okay. I don't know why they even spent the time to do it, but they did. Okay, now we move on to the next slide. Integration as an accumulation process. Isn't that what we were doing? I mean, you're going from this value to that value, accumulating the delta x's, okay? You're integrating over that. But in this section, the integration formula for an area between two curves was developed by using a rectangle as a representative element. For each new application of integration in the remaining sections of this chapter, an appropriate representative element will be constructed using pre-calculus formulas you already know. Each integration formula will then be obtained by summing and accumulating those. Okay. I'm not quite sure I'm following what they're saying. For example, the area formula in this section was developed as areas equal height times width. Okay, we got that. I'm not sure I'm following what they're saying here. Let's see if we can do it. Oh, here's all this. I was reading that, and here it is there. Integration formula for the area between two curves was developed using a rectangle as a representative element. For each new application of integration in the remaining sections of this chapter, appropriate representative element will be constructed using pre-calculus formula you already know. Each integration formula will then be obtained by summing the accumulation or accumulating these representative elements. Okay, what's different? The known pre-calculus formula, representative element. Okay, I guess there's going to be something that's going to be obvious here. For example, the area formula for this was area's height times width, which delta A is your difference of F and G, assuming F is the larger, G is the lesser, times your delta X, and that then became your integral. Okay, got it. What's new? Okay. So here's example 6. Maybe we'll see it. Find the area of the region bounded by the graph of y is equal to 4 minus x squared and the x-axis. Describe the integration as an accumulation process. It's what we've been doing. I mean, maybe I jumped the gun on it. I don't know, but here's your, let's draw the graph of it. I know, but that's what I've been doing. So I'm sorry, I already was doing that. That's the only way that makes sense. How would I graph this? Give me a few points. Okay, x equals 0, y is equal to what? 4. Okay. Okay. So 0, 4. Negative 2. 0 and positive 2, 0. Okay, they're basically, and 1 will be 3 and or negative 1 and 3. Okay, all right. So it says find the area of the region bounded by the graph of y is equal to x 4 minus x squared and the x-axis, which is what we got there. So we're only looking at this area here, okay? So again, I didn't know we weren't supposed to be doing this. We pick a dx, okay? Or you could choose dy if you wanted to, but please don't, okay? And what's the area of that rectangle? We've been doing this all along. 4 minus x squared. Minus 0, so 4 minus x squared times dx, okay? And then we're going to, I jumped right over into the to the integral, the a would be the integral from what to what? Where's your x going from to? Negative 2, 0 to 2, 0. Okay, this is 0, 4. Okay, so this will be going from negative 2 to 2. What's your integrand? Four minus x squared dx. Now, time out. Did I talk to you last time about what I thought it took to be a good mathematician? What? To be what? Just a little lazy. I want to be pretty lazy on this one because I look at this, I know parabolae are symmetric about the axis of symmetry. That's why I call it axis of symmetry. They're symmetric about it, right? And so this, that is the axis, the y-axis is the axis of symmetry. So what can I say about this area? It's twice what either one of those is, right? So let's not go negative 2 to 0. Let's go 0 to 2 and double it. So put the 2 out here and put the 0 here. Now, why is 0 easier than negative 2? I thought negative 2 was a smaller number. Yeah, 0, I even can evaluate that one. So let's do it this way. That would be, so we're not doing what the book says to. Okay, sorry about that. Get over it. What's the antiderivative of 4? 4x minus x cubed over 3, evaluated from 0 to 2. Don't forget the 2 out front because that's what allows us to do that. Get out of there. Okay. So it'll be 2 times what? 8. Just 8. Okay. 2 times 4 minus 8 over 3. Okay, which you could say that's 2 times 24 over 3 minus 8 over 3, right? And 24 minus 8 is 16 thirds. So this will be 32 thirds. So just a little over 10. 32 thirds. Okay, and I found this somewhere here. Yep, that's what they got. Good for them. Now, I'm not sure they did it that same way. No, they did it awfully close. They just went from negative 2 to 2. Still works, okay? But if you're doing that and you come up with a 0 area and you see this, that's not a 0 area. So the odds are you added where you should have subtracted or vice versa, okay? So watch those signs. That's the other thing of doing it this way. You remove half of the signs, the ones that are most likely to trip you up. So use symmetry if you can. That finally finishes 7.1. Okay? Oh, wait. Let's go back and see how they did it. Because I think they do it. What's that? Yeah, exactly. So the area is that. They went straight to that, and they did the minus 2 to 2. And you can think of the integration as accumulation of the rectangles, which of course that's what we were doing with negative 2 to 2, as shown in this figure. So sure enough, we're going to add all these little rectangles. But that's what we're doing. That's what the integral sign does. It sums them up for you. Okay? Oh, you're kidding me. But they really don't. If they were doing that, they would do minus 2 to minus 1, minus 1 to 0, 0 to 1, but they don't. They do their integration all the way across. They don't accumulate them. They just say this is what it turns out to be, which is fine, but boy, what a pain in the neck way to do it. It's just a lot of extra work.
Maybe we just try to teach us to get through that.
What's that?
They're doing it one by one.
Yeah, but they they let that go and accumulate as it goes. So they just say 1, 2, 3, 4 extra intervals where they could have just done the one, or take half of it and done that.
So is that like a proof?
No, I don't know what it's like. It's just the way they chose to do it. This is my first time of teaching this text with this course, and I like the author okay, but this to me is, it comes close to just being silly. I mean, I don't know. I don't think you'll ever have to do that. If it helps you see something, by all means follow up on it, okay? But that's why when he first started talking, what is he accumulating except your DXs? And now he's just marching you through the process, which is fine, good. Just a lot of extra work. Okay. All right. Homework exercises in this section. Do any of the odds 5 through 9. All the odds are at calcchat.com. Number 7's at CalcView. Do either 11 or 13. They're both at CalcChat. 11's at CalcView. Do any of the odds 15 to 27. They're all at CalcChat. 17's at CalcView. Do 29. It's the only one. It's at both CalcChat and CalcView. Do any of the odds 31 to 35. Now it says you need graphing utility. I don't think you do, but if you do, use it. But I think you can get by without it. Do any of the odds 37 to 41. They're all at CalcChat. Only 37's at CalcView. Do either 43 or 45. And again, they say you need graphing utility. It may be sort of difficult not to, but try it without. If you got it, use it. They don't have any of those at CalcView. They're all both at CalcChat. Either 47 or 49. They're both at CalcChat, not at CalcView. And they say you need a graphing utility there too. I don't know that you do. And then number 51. Do that one. CalcChat. 53 or 55. 53's at CalcChat. Both of them are CalcChat. 53's at CalcView. Do either 57 or 59. They're both at CalcChat. Neither at CalcView. 61 or 63. They're both at CalcChat. Neither at CalcView. And then they're exploring the concepts. Good things to think about. 65 and 67. Read through. Ponder them. You don't have to do anything with that if you don't want to. 69, I think is an okay problem. You can probably do 71 and 73. 75. These are a little bit different kinds of problems, but I think you can still do them. Number 77, I don't mean that you have to do it, but one reason I'm going to point it out is talking about a Lorentz curve. Well, anytime you see something named like that, there's a pretty good chance that it's named after somebody. So if you wanted to consider who was Lorentz, how did he develop, or why did he develop this curve, what's it used for, that kind of stuff, you could get 1 or 2 or 3 paper topics out of that. Okay, 79 is a building design type problem, which if any of you are going into that kind of engineering, you might find that of interest. 81's an area type problem, which looks a little hairier just because it's using pies and things like this, but I believe it's a pretty straightforward problem. And then there's some true-false, either 83 or 85 are true-false. I don't know if these are CalcChat. They should be. Now, I don't know if I've mentioned to you before, this book has the Putnam Challenge. That's some sort of big math competition they have. These are usually pretty hairy problems, but if you want to pursue one or more of those, you certainly can. All right, any questions then on 7.1? So let's move on to 7.2. And like I said before, I did load all the PowerPoints from all 5 chapters that we might be covering, though I know we're not going to have time to do all of them. But here in 7.2, we're certainly going to do volume. And there's two methods that we use to calculate volumes. Well, there's other ways to do volumes, but let me, what I mean by that, volumes of rotation. Okay. Okay. So these are continuing with applications of integration. We did areas. Now we're going to do some volumes. Now these are volumes of revolution, not just any old volume, volumes of revolution. The first method we're going to learn is the disk method, and we'll find the volume of a solid by solid of revolution using the disk method. We'll find the volume of a solid using the washer method, which is very similar, and we'll find the volume of a solid with known cross-sections. Okay? Which sounds a lot like the other two, but we'll see what they mean by that. Let's start with the disk method. All right. When a region a plane is revolved about a line, the resulting solid is a solid of revolution. So think of this. Here's a line, and this region, is a simple rectangle. Okay? The rectangle has a width, they're calling W, clever name, and height, you might say, or length of R. That capital R doesn't stand for rectangle. Okay? Capital R stands for radius, because you're going to revolve that around the x-axis, the axis of revolution. And what you're going to do is a big chunk of cheese there. Okay? And you revolve that around the horizontal axis, or whatever axis that is. And then you're going to have a disk. Well, that disk, okay, is a very short disk, because that W was pretty small. And that capital R is now that was your Y value above this axis of revolution, so that's going to be the radius of that disk. Okay? And what's the volume of a disk? And I'd rather call this a right circular cylinder, because that's what we're used to calling it. It's the area of the base, which is pi r squared, and that is your capital R there, times the height, which is your W. Your right circular cylinder like that. So that volume of the disk is pi r squared times the height. Okay? The simplest such solid is a right circular cylinder, okay, or disk, which is formed by revolving the rectangle about an axis adjacent to one side of the rectangle, as shown here. Okay? So the axis is adjacent to one side of the rectangle. That means that's where it ends, revolving that around. This could also be, if this would be your vertical axis, you could have revolved it this way. That would have been your Y, that would have been your W then. So you could do other sides of this. Now, if this is just a lot of blah, blah, blah to you, then yeah, I understand that sort of. But if you start picturing things, if now rather than a rectangle, you actually have a curve, but you're going to approximate that by little rectangles, now your W is going to get narrower and narrower, and that might be your Z-axis here. And if it's a curve, that's going to come closer and closer. The thinner that is, to actually reading that, you're going to sum those or accumulate those from one endpoint to the other. That's where we're heading on this. Okay? The volume of such a disk is the area of the disk, that's the pi r squared, times the width of the disk, which is your W. Where R is the radius of the disk and W is the width. Wow, they just now got around to telling us that. So, what if we have, here's what I was just saying, what if we have a curve like this that we're revolving around the x-axis? That's going to make a nice Christmas tree stand, right? Or something like that. And what we're going to do then is it's hard to do that little thing, so we're going to do little rectangles to approximate those areas and approximate the volume, and then like the rectangles get smaller, thinner and thinner and thinner, just a lot more of them, and that's going to come closer and closer to the volume of representation. So you let the delta x reduce to a dx, and then you integrate from A to B. Make sense? Yes?
Can I come to the last slide real quick? Can you go back to the last slide?
Yeah, sure. That one?
Yes.
Oh, okay, I'm sorry. If I go too fast, get off on too soon, stop me, slow me down. Usually I'm moving awfully slow to begin with. Sometimes I go too fast. And I shouldn't have even mentioned the y because that has the dy's, the way I was talking before, is way too thick. This one at least was represented this one. Okay?
Yes, sir.
Everybody got it? All right. How about this one? Need a little more time on this. So, everybody got this one? Okay. Now, this is showing finite delta x's here. Now, obviously, that's not going to be the same volume as this, but if you let these get smaller and smaller and smaller, it gets closer and closer and closer to that until you let your delta x infinitesimally go to a dx, and that then gives you your integration. Not a summation, but an integration. And that's exactly what we're doing here. Now, let's see what if you're revolving around here, your radius again is that, and your width becomes the dx, delta x, which ultimately becomes dx. And the summation of those will become the integral. So to determine the volume of a solid, consider the representative rectangle in the plane region. Now that rectangle is revolved around the axis of revolution. It generates a representative disk whose volume is, now you see this is a delta volume, because you have a delta x there, but the radius of that is going to be pi capital R squared. Now, anyone want to predict what that R is going to become? What that's going to be? Especially going back to this figure. This is going to be your function. Alpha beta. The y beta. When it's drawn like this. Later when we do it around the y-axis, it will be your delta x. I mean, it will be your x is a function of y. This will be y as a function of x. That's right. So we're going to be squaring our function, is what I'm getting at. Okay. So to determine that, that is revolved around, that's what you're going to do. Pi r squared comes to delta x. Approximating the volume of the solid by n such disks with width delta s, okay, and the radius r, which is some function of your x of I, your function comes into play. That produces the volume of the solid as being approximated by the summation from I is equal to 1 to n, you don't do n of these little disks, pi times that function squared times the delta x. Okay? The pi is just constant. It can come outside the summation, and it'll be r as function x of I, whatever interval you have to be on squared, times the delta x. When you see it now, feel it coming, pi times the integral from a to b f of x squared dx. That's where we're heading. That approximation appears to be better and better as your deltas get smaller and smaller and smaller, approaching zero. Of course, that makes your n going to infinity. So you can define the volume of the solid as the limit as your delta x, the deltas, in this case it is delta x, are going to zero. Your n's are going to infinity, pi times integral of, and that's your function value squared times your delta x. This then goes to pi times sum goes to an integral from one end to the other, okay, r of x squared becoming f of x. schematically, the disk method looks like this. The known pre-calculus formula, V is equal to pi r squared W, representative element, this is probably why they did the other thing, I guess. It becomes a delta V, which is pi times your r of xi squared delta x to the new integration formula, V is equal to pi times the integral from A to B, first endpoint to last endpoint, r of x squared, which this will become your f of x, dx. The r of x becomes f of x, so it'd be f of x squared. All right, now, similar formula can be derived when the axis of revolution is vertical. Okay? If you're going around the horizontal axis, do your d's that way, because that's your width of that. But when you're going across the vertical axis, then do a dy. Then you have to get all this function in terms of x as a function of y. So this has to be r of x. So r of y. Because if you're doing a dx here, this has to be in terms of x. If you're doing a dy here, this has to be in terms of y. That just becomes necessary. Otherwise, it's really hard to calculate. And this will do the disk method. So to find the volume of a solid of revolution by the disk method, use one of the formulas. So this will be it for the horizontal axis of revolution, pi integral from A to B of r of x, become your f of x and d of x, so like this, squared dx. And if it's around the vertical axis, it's pi times integral from c to d. So these are the limits on the dy. So again, if you choose a dy here, you have to use limits from c to d. That r of y, which now is x is a function of y, okay, squared dy. So everything is proportional. Getting that change from y as a function of x to x as a function of y, that becomes almost the most difficult thing and the thing you have to really pay attention to. So here's example 1. Find the volume of a solid formed by revolving the region bounded by the graph of f of x is equal to, see, I told you it was going to become f of x, square root of sine x, and the x-axis, x is going from 0 to pi, about the x-axis. So the x-axis is the base of that formula, but it's also your axis of rotation or revolution. Okay, so this is what we're doing. F of x is equal to square root of sine x. Now, I don't know if you have a good idea what that is. Do you? It's not. It almost looks like it's one lobe of a sine function, but it's not. It's the square root of a sine function. Okay? And that solid of revolution is looking a lot like a sphere. Is there any reason that should be a sphere? Maybe we shouldn't go there yet. It sure looks like it could be one. Okay? Let's see what happens. All right. What would be your, goodness gracious, how it looks there and how it looks on my slide is very, very, very different. Let's see how it looks in the book. That doesn't look any like, oh wait. No. That to me doesn't look anything like the figure in the book. I mean, a little bit, but not much. Okay. That to me looks almost spherical, not quite. This is very football shaped, okay, or rugby ball shaped or something. Okay, so let's do this. So it's nothing like a sphere. So what would be your procedure? Where would you go? Whoops, let me get my, sorry, I forgot. I'm not, okay, say again. Okay, so what would it look like? V is equal to pi, 0, the integral of 0 to pi. Okay, the square root of sine x squared dx. All that's going to come out pretty nice, isn't it? What's the square root of sine squared? All right, so this is going to be pi times the integral from 0 to pi of sine x dx. I think we can do that, can't we? Pi times, what's the antiderivative of sine? Negative cosine. And that's evaluated from 0 to pi. Okay, this is going to be pi. Okay, and what is minus cosine of pi? Well, let's just start. What is cosine of pi? Negative 1, and minus that would be 1 minus a minus, which is a plus, right? So that's going to be plus the cosine of 0. And that's 1. So this is going to be 2 pi. Okay. Without knowing what the shape is actually going to be, and maybe it's just off my perspective. Yeah, that does look a lot more like that. From over there, that is probably spherical. Okay. But we get a volume of 2 pi. And let's see. Oh, that's what they got to. Good for them. Okay. Now, let me delete. I'm rapidly running out of energy, folks. Sorry about this. I had no lunch yet. Okay. Let's see how they proceeded. They said from the representative rectangle, there's that little rectangle there, there's your dx. You can see that the radius of that solid would be the f of x. Okay? That's going to be the square root of sine x. The radius is your f of x. Okay? Which is square root of sine x. But you're going to take, to get the volume, is going to be pi times the integral from a to b of that radius squared, which is square root of sine squared, which is just sine x dx, and that's what you get here. And then you do the antiderivative, that's going to be your pi times your negative cosine, evaluated from negative pi to 0 to negative pi, and that's going to be pi times a positive 1, a minus 1, which is positive 1, minus a minus, which is plus, that is another 1, and that's going to be pi. All right, watch those signs. All right. Let's do example 2. They don't do example 2, so let's us do it. Find the volume of a solid formed by revolving the region bounded by the graphs of f of x equal 2 minus x squared. Okay? And g of x equal 1. Okay? Find the volume. Excuse me. Bounded by the graphs of that and g of x equal 1 about the line y equal 1. That's your axis of rotation, as shown in the figure. Yuck, they're going to make me draw the figure, aren't they? All right. It'll be a quick rendition of it. Okay? So your y is equal 2 minus x squared. Okay. Here's the line y is equal to 1. That, or g, let's g of x equal 1. Okay. That's that line. The other's up here at 2. When x equals 0, that's 2. When x is equal to 1, you'll be plus or minus 1. Okay? And this is a parabola that's something like that. Okay? If you, goodness gracious. If you continued on down, this is going to be square root of 2 down here, minus and plus the square root of 2, because square root of 2 squared minus, would be 2. 2 minus 2 would be 0, so that would be on down there. We don't need to do that, though. We stop right there because that's the volume revolving around this line here, so that means the bottom half looks just like the top half. Okay? Now, again, why in the world did they do the very easy one on the slide, and this one's introducing at least 2 new concepts. The other one had the x-axis as the axis of symmetry, the axis of rotation. This one has the line y equal 1, or g of x equal 1 as the boundary and also the axis of rotation. Okay? So what we're going to have to do then, let's do our little rectangles. That's where these rectangles come in handy, and make sure we're thinking through things. So sure enough, your thickness is dx. That makes sense. But what's the length of that radius? That would be your f of x, that's this curve here, minus g, minus 1. Exactly. Okay? Minus g of x. So your radius here, I'm going to call it r of x because that's what they were calling it before, would be 2 minus x squared minus 1, which if you carry that out, that would be 1 minus x squared. So there's the radius function. Okay? Now I think we're ready to go on it. Okay? What's our integral? Well, let's do the volume. What's that formula? Pi, that's in front. Okay? Times the integral. Okay. Okay, you're saying 0 to... I agree with you because we can just double it. Let's just go 0 to that. Now, we don't have our endpoint there, or do we? The x is going from 0 to 1. Minus 1, because I said already, this is the point where... what was I saying? This is the parabola. Where it intersects the line g equal 1, that's it. 1, 1, a negative 1, 1, and a positive 1, 1. So let's just go 0 to 1. Okay? We're going to need a 2 in front because we're having the things to 0 to 1. And then this is our r of x. Not either function they gave us up here, but the difference of those functions. So it's a 1 minus x squared dx. Perfect. What do we better do first, though? Okay, yeah, let's square that 1 minus x squared. And what does that give us? 1 minus, a little louder, minus 2x squared plus x to the fourth. Okay, times dx. Now just notice someone got up to, I guess, take a little break. And I told my last class this, I don't know if we talked about this before. This is 2 hours and 40 minutes of class, solid. That's a lot. Especially if you grab lunch beforehand, you might need a break. So anytime after an hour and 20 minutes, which would be for us after 12:20, and we're past that now, do we want to take a break?
Yes.
Okay, let's try to keep it less than 5. Do you want to finish this problem first or go on and finish the problem? Okay. Since we got it all set up, ready to go, let's do our integration. 2 pi, the 2 because we doubled it, we're only doing 0 to 1. Okay, and what's the antiderivative of 1? X. Next. Minus 2x cubed over 3 plus x to the fifth over 5. Evaluate that from 0 to 1. Okay? So that's going to be 2 pi times, plugging in the 1, what do we get? 1 minus 2/3, 1 over 5, and guess what? I can do the zeros, 0. Okay? That's it. So this will be 2 pi times, let's get least common denominator of 15. It'd be 15 fifteenths minus 10 fifteenths plus 3 fifteenths. Right? So that's 18 fifteenths minus 10 fifteenths would be 8 fifteenths, and double that and you have 16 pi fifteenths I think that's what we get. Let's see. Yep, 16 pi fifteenths. Okay. So let's go. Next thing we'll do is the washer method. So let's go to that slide. So when we come back, we'll be at the right. Any questions on that before we leave it? Okay. So we're going to pick up with the washer method. I'm going to pause this. Now here's the thing, folks. Remind me to take this off pause. In other words, get your pause off. Okay. All right. So what we've done up till now was what they call the disk method, which basically meant, now originally we started off with the horizontal axis, a horizontal axis being the bottom, okay, of your rectangle, and you're revolving that around. If that's the x-axis, then your height is your f of x, okay? So then in that last one, we moved the boundary up to be the line y is equal to 1, and we just took part of the rectangle, of the parabola that went down to that, but then revolved around that y is equal to 1, okay? This time we're going to do something that's sort of a hybrid between those two. We'll have the region up here, okay, will revolve around down here, which means you're doing the difference between this function and doing the revolution around there. It's going to leave a hole in the middle, and therefore the washer method. It's a disk with a hole in the middle. So it's a difference between two curves, okay? Let's see how they explain it. The disk method can be extended to cover solids in revolution with holes by replacing the representative disk with a representative washer, okay? The washer is formed by rotating a rectangle about an axis, but not an axis that's on the boundary of that rectangle. The boundary of the rectangle is off the axis of revolution, and that leaves you a lifesaver, okay, or something with a hole in the middle, okay? Now, Here you notice you have two radii, the outer radius and the inner radius. Okay? It's the distance between the two that makes for the solid, but you have to use both of them. Okay? And it's the bigger minus the smaller, and that gives you that wedge there, that's the part that you're revolving. Okay. If R, little r and big R are the inner and outer radii of the washer, respectively, and W is the width of the washer, then the volume of the washer is pi times the difference between those two squares times W. Now, if that's not making a lot of sense to you, think of it this way. Extend that rectangle on down here, and you have a pi r squared W, just like we did before, right? And then you're going to subtract out this part right here, around there. So minus pi little r squared W. And then the pi and the W are the same common term, so it's the difference of the two radii. But it's basically because you're doing a big washer subtracting off the small washer. Okay. Either way you want to look at it, whatever helps you see it best. For some reason. Okay. All right. To see how this concept can be used to find the volume of a solid of revolution, consider the region bounded by an outer radius r of x, inner radius little r of x, shown here. So here we have a here is your outer radius, the capital R. Okay? Here you have your inner radius, little r, and these are both functions of x. You're revolving those around, say, the x-axis. Okay. Kind of a megaphone-looking thing, only it's a truncated cone on the outside, but got some curvature on the inside, which may project the sound better, I don't know. Okay? So that's what you got. Well, what are you revolving? You're revolving the capital R around, subtracting off the little r around, or just think of this as the difference between capital R and little r. But don't think of that as being the thing squared. It's the capital R squared minus the little r squared. That's the difference here. Don't subtract before you square. Don't square the subtraction, subtract the squares. Okay? If that makes any sense. Okay? If the region revolved around the axis of revolution, then the volume of the resulting solid will be pi times the outer radius squared minus the inner radius squared times dx. Think of this as the outer disk minus the inner disk. Okay, that gives you your volume. Note that the integral involving the inner radius represents the volume of the whole that is subtracted from the integral of the outer radius. Okay, kind of what I just said, only different terms. So here's example 3. Okay. Find the volume, okay, same for you. Find the volume of the solid formed by revolving the disk bounded by the graph of y is equal to the square root of x. That's this function. Okay? And y is equal to x squared. That's that function. About the x-axis is shown here. Okay? All right. There we have it. Now, for one purpose, this is really instructive. You know, it shows you dx here and that part of the stuff. But for the other part, your height is not the difference between these two like we've done before. What you're doing is one r squared minus the other r squared. So for the other reason I don't like that, because you think that's the height being squared, you know, that part being squared, it's not. It's the upper part minus the lower. The upper part squared minus the lower part squared. Okay? So, what is the upper part? Y is equal to square root of x. But when you square that, you get x. Minus the lower part, which is y is equal to x squared. When you square that, you get x to the fourth. Okay? So what your integral then is what? The volume is equal to what always comes first? Pi. Okay. Usually you save that for dessert, but it comes first. Okay, never mind. The integral from where to where? Oh, and we didn't do this. We probably should have. The area bounded by that region, when you set x equal x squared, you got to find the points of intersection. Actually, 0, 0 is 1. And just pretty obviously, too, 1, 1 is 1. But when you set those equal to each other, you square both sides, and you get x equal x to the fourth. So x, let's do x to the fourth minus x equals 0. Square root of x equal x squared. Square both sides of that, you get x equal x to the fourth. And then subtract and do x to the fourth minus x equals 0. Okay. Then factor x times x cubed minus 1 equals 0. Obviously, x equals 0 is a solution, and the only other one is x cubed equal 1, which would be x equal 1. So 1, 1, and 1, 1, 1. Yeah, 0, 0, 1, 1. You go back and plug these in. 1. You plug in a 0, you get 0. You plug in a 1, you get 1. There you get a 1. So 1, 1, and 0, 0. A lot of blah, blah, blah. Okay. So your interval, since you're doing dx's, is 0, x equals 0 to x equal 1. And what's your differences here? Basically, almost what I just did. Your upper one is your r squared or your y squared is x minus your lower one is, because you got to square these, remember, it's y squared and y squared equal x to the fourth. You're squaring these because this is your capital R, this is squared, this is your r, this is your little r, so your little r squared is equal to that. So what's your integrand?
X to the fourth.
X minus x to the fourth dx. Only thing that rectangle is giving you is your dx, in my mind. Okay? So what does this give you? Pi times antiderivative of x. X squared over 2 minus x fifth over 5, evaluated from 0 to 1. It'll be pi times, you do the 1 part, I'll do the 0 part. Second?
1/2 minus 1/5.
I can't hear.
1/2 minus
1/2 minus 1/5. Okay, thank you. I'm just hard of hearing. Okay, 0 is 0. So that would be pi times, that would be 5/10 minus 2/10 is what?
Is it 3/10? 3 over 10.
3/10. Okay, okay. 3 over 10. So that would be 3 pi tenths, or 3/10 pi, or however you want to say that. And that's what they got, 3/10 pi. Yeah. Question? Okay. All right. And guess what? You can revolve around the vertical axis just as well. Oh, wait. They showed this. Let me show the rest of the problem the way they did it. Okay. In the figure you saw before, you saw that the r of x is square root of x, capital R, the big R. The little r is x squared. Okay? So when you square each of those, integrating between 0 and 1, they didn't show you where they got that, but we did. Then that would be pi times the interval from a to b, which this time is 0 to 1, and your capital R squared, which turns out just being x, minus little r squared, which is x squared squared, which is x to the fourth. So that's the integral of pi times the integral of 0 to 1 of x minus x to the fourth dx. The calculus is the easy part. Okay, setting it up is a hard part. And it's not that hard. And that would be pi times x squared over 2 minus x fifth over 5 from 0 to 1, which is 3/10 pi. Okay. All right. In each example so far, the axis of revolution has been horizontal, and you've integrated with respect to x. Okay? In the next example, example 4 coming up, the axis of revolution is vertical, and you integrate with respect to y. In this example, you need two separate integrals to compute the volume. Now, that's not because it's y. It's because of the problem. So don't think anytime you're doing it with a vertical axis, you're going to have two. It's just the nature of this problem. Okay? So let's see what the problem is. What's your problem? Okay. Find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x squared plus 1. That's this curve. Y is equal to 0. Oops, that's this curve. That's the straight line, the x-axis. X equals 0. That's the y-axis. And x equal 1. That's this line right here. Okay? Here's why you're having to integrate twice. Okay? This is rather a poorly worded problem. That's not bounded by x equal 1 anywhere. That's just a line there. They put that in to make it make sense for you. The bounds are right here. Okay? You would have to figure out, you've got to put that line in there to do your problem. But that's not part of the bounding. Okay? But you would have to put it in to solve your problem. So to me, that's a little misleading there. The bounds are these two. Okay? Here, here. Oh, no, I'm sorry. X equal 1. That's that bound. Yeah. You got to have that bound in there. I thought they drew that line, but that's y is equal 1. Okay. All right. Yeah, they're right. That line, and that line. Yeah. You need 4. Okay? Now, the reason you have to do two integrals, two integrations, you do this part and that part. You can't do them the same because your delta y, your rectangle, of course, is a delta y here, That's the same, but here it's going from y equal 1 to this, and here it's doing y is equal 1, y equal 0. Well, this is just a disk, just like we were talking before, radius of 1, width of 1, okay? That's just a right circular cylinder, that part down there, okay? This one, the outer radius is 1, the inner radius is this. But, here's the problem. Anytime you do the dy's, no, not anytime, this kind of problem, when you're doing the dy's, then you have to get x as a function of y, not y as a function of x, okay? Because you need the dy by itself. So what you have to do here, of course, I know this is way too easy, solve for x. First thing you're going to do is subtract 1 from both sides. So you have x squared is equal to y minus 1, and then take a square root. And that would be x is equal to the square root of y minus 1. Now, which square root? Usually when you take a square root of both sides, you do a plus or minus. Which one are you dealing with here? your x's are between 0 and 1. So that's the positive square root. Not all problems would be that way. You have to pay attention to that, and this would be x as a function of square root of y minus 1. The reason for that, you're all positive x's are between 0 and 1. Okay. So there's actually a couple ways you could have done this. You could have done the entire cylinder here and then subtract off this part, or do this cylinder here and just do this part over here. The way they're setting it up, they say go this way. Either way will be fine. All right? You tell me which you want to integrate first. The upper part, the lower part, the big part, small part, how you want to do it.
We do upper.
Second?
The upper part.
Upper part. Okay, so how would that go? We'll call that V1. Okay? This part right in here is V1. Okay? What would V1 be? Pi. Good. Okay? Integral. Second, from 1 to 2. You're doing dy, so you need to be from 1 to 2. One. 1 squared is 1. Minus. Second.
X squared plus 1 squared.
Oh.
Y minus 1.
Yeah, and that'll be minus y minus 1, right? Which, ding, that's just the integral of minus y dy, right? That didn't turn out being a bad integral at all. So let's see what that gives us. Pi, what would that be? We can even bring the minus outside if you wanted to, just because it is a minus in there. Antiderivative of y. Y squared over 2, evaluated from 1 to 2. Okay? That'll be a minus pi times woo! Second? Okay. 2 minus 1/2. Is that what you said? Yep. Okay. Which will be, this is coming out really strangely. This is not making any sense. You're coming up with a negative volume, which most states is not allowed that, okay? Where have we gone a little bit wrong here? Parentheses. That's where it messed up. It's 1 squared minus this thing squared. That belonged in parentheses. You see? Watch these. Those signs will get you. Okay? And this, you can't subtract now. This is minus and minus is plus. So let's erase everything from that point on. In fact, whoops. Eraser didn't pick up. Okay, there we go. So, pause yourself anytime you happen to see a negative volume, a negative area. Those are not too good of things to have, right? Oh, I erased more than I should, but that's okay. We're not using that anymore. Okay, so this will be the integral pi times the integral of 2 minus y dy. So let's integrate that one. Pi times 2y y squared over 2, evaluated from 1 to 2. Okay? So it's going to be pi times 4 minus 2 I want y'all to get the signs right. Next. Don't you like it when it's a 0 there? It's not a 0. What do you have? A minus 2 and then a plus 1. Okay. You see why that's true? Okay. This is the plus with the 2 there. 2 times 2 is 4, minus 4 squared over 2 squared over 2, which is 4 over 2, which is minus 2. Then when you do the lower one, you negate this, so it's a minus 2 times 1, which is a minus 2, minus a minus 2 times, okay, and you plug in a 1 there, and you get a plus. That's a 1/2, isn't it? Yeah. I thought someone said 1. Okay. Okay. And this adds to 0. And you get pi halves. That's the volume of that first part. Not that big of a volume. Now, how do you want to do the volume of the bottom part? Yeah. Let's do the area of the bottom, which is pi r squared, where r is 1. So pi times 1. This is pi, isn't it? Okay. So that's half a pi plus a pi. Oh, that doesn't seem right, is it? It's 3/2 pi. And that's what they got. Okay, so the bottom part here is pi times 1 squared times 1, which is just pi plus pi halves is 3/2 pi. Now, for the life of me, I was thinking when I looked at this volume looks like it's a lot less than that volume, right? So that doesn't look like it would be half of this. But if you think about it, this part's being revolved, and this, sure enough, that is half. This part revolved around this part is half of that radius for most of them. That was a surprising thing, just looking at it. Okay, so let's see how they did it. The region shown by the outer radius is simply r is equal to 1. There is, however, no convenient formula to represent the inner radius, so you have to go back and do that, and that is square root of r minus 1, which we did too. Okay, and then, so it's your inner radius is 0 for the bottom part, and which is really interesting, and square root of y minus 1. I never would have thought to phrase it that way, but it's okay. So it's that top part doing 0 squared. That's really important. You just get pi. Okay. And the other part you get 2 minus y, and we did that integration and did the evaluation. There was exactly what we got, and that came up 3/2 pi. So good for them. Everybody see that? This is just a slightly different. Do I need to go back and do that more slowly for some? You okay? Okay. Note that the first integral, pi from 0 to 1 to pi, represents the volume of right circular cylinder of radius 1, height 1. That's what we did. Okay. The portion of the volume could have been determined without using calculus. That's what we did. Okay. Now, all right. They skip example 5. Let's see about it. I have a feeling that's a lot more. And this one is also at larsoncalculus.com. So he seems to be putting these that he doesn't show on the slides, whether he decides what's on the slide set or not, I don't know. Okay, a manufacturer drills a hole through the center of a metal sphere of radius 5 inches. Okay. That's not the best wording, okay, until you read the next sentence. The manufacturer drills a hole through the center of a metal sphere of radius 5 inches. When I first read that, I thought, is the sphere radius 5 inches, or is the hole radius 5 inches? Then the next sentence he says the hole has a radius of 3 inches, so it's a sphere with a radius 5. What is the volume of the resulting metal ring? Okay? Now, you might be tempted to say, oh, we can do the volume of the sphere and subtract off the volume of a cylinder. Will that give it to us? What's wrong with that picture? That cylinder has rounded edges. It's not a cylinder. It's not a right circular cylinder. So no, you can't. You're going to have to use calculus to get it. You can't do it strictly without. In fact, I don't think you can do any part of it without. Okay? So, what you're going to have to do is draw a picture of what's left, of a cross-section area of what's left. So let's do the best rendition I can, which isn't very good, of, we'll try to start with 5. That'll be 2 and 3 and 4 and 1. 5, 2 and 3 and 1 and 4, something like that. 5, 2 and 3 and 1 and 4. 5, 2 and 3 and 1 and 4. Okay, we'll try to start with imagine that's a sphere, not a very pretty sphere, okay? But then we're going to have a radius 3 hole drilled into it, okay? So you lose this part altogether. See, that's where you can't take the difference, okay? You either have to account for this part you're losing out here and then use just that part of your thing. So that really the easier part would be do your little disc like this, or washer like this. The outer radius is, what is the radius of that sphere at any value? We're choosing to do a dx, which I think is the right way to go. What is the outer part here? What's the area of a circle? Second? Okay. X squared plus y squared is equal to, it would be 5 squared, right? So your y in terms of x would be y is equal to, well, let's just, y squared is equal to 25 minus x squared, right? And then take a square root, and we're only going to take the positive because we're going to take this upper part. Y is equal to the square root of 25 minus x squared. So there's the upper part of that. The lower part is just going to be y is equal to, and literally you're going to be subtracting off this part in here, and this is just, the inner circle is y is equal to 3, right? So that's not too bad, okay? Now, what is a little different is where your x is going to. You're doing dx's from, and let's just go 0 to out here and double it, because that will all be the same. Where is out here? Okay, where does that reach it to?
We can't go positive or negative 5.
Say again?
So we can't go positive or negative 5, so then it's 0 on the square. So then
Yeah, because you don't ever reach there. Okay, you're only going to there. But what we do know is this is 5. This diagonal here, I don't want to call it R. What do we want to call it? D for diagonal is equal to 5. And this is 3. This is our little R3. We can call that 3. Okay? And so what's our x going to be? Ah, yes, it's a 3, 4, 5 triangle, isn't it? I almost got it right on my dimensioning there. So this is your x is only going, well, this x is equal to 4. Okay, so we do now have it. Thank you very much for this 3, 5, 4, 5 triangle. Okay, so what is our volume of that ring that's left? Pi, okay, that's the hard part. Integral from 0 to 4. Oh, and we're going to double it, so let's put the 2 out front. We're going to be really lazy, right? Okay. And 25 minus x squared, because you got to square that, remember? Minus 3 squared is 9 dx. I usually like to do that beforehand, so I can just write down my integral. V is equal to 2 pi integral from 0 to 4. Okay? And this will be 16 minus x squared dx. Okay? Do the math. 2 pi times antiderivative of 16. 16x minus x cubed over 3, evaluated from 0 to 4. And this will be, I'll keep it this way, 2 pi times, help me, 64 minus 64 thirds. Got it? Done. And that will be, say again? I can't hear it. Okay. It's 2 times 64 thirds. Is that what you said? Yeah. Okay, so 2 pi times 128 thirds, which will wind up being 456 thirds pi. No, that can't be true. 256, sorry. I said it can't be true, yeah. 256 pi, because 3 won't go into it. We know that. Yeah. 256 pi thirds. Cubic inches. This, by the way, they did have dimensions. So usually if there's dimensions, let's keep the dimensions. Okay. I'd forgotten they did say inches. They did. All right. Good deal. Thank you for making that a 3, 4, 5 triangle. I wondered why they chose those. That's why it is. All right. So that's example 5. Let's move on to solids with known cross sections. Okay. With the disk method, you can find the volume of a solid having a circular cross section whose area is A is equal to pi capital R squared. With that, you know that radius. Okay. Sure. Okay. This method can be generalized okay, to solids of any shape, as long as you know a formula for the area of the arbitrary cross-section. Some common cross-sections are squares, rectangles, triangles, semicircles, and trapezoids. Yay. Okay. So here are a few of those. For a cross-section of area A of x, taken perpendicular to the axis, the volume is the integral of that area. I'm trying to find the word. Okay, right here. This first picture doesn't really fit what they've been saying, I don't think. That one fits perfectly. That one's perfectly fine. Okay? This one, that's not a regular cross-section. Okay? That I can see. Because this would be, looks like it's going to be a rectangle here, except it has a curved surface there. That would be perpendicular to the x-axis. This doesn't fit this at all. With the same shape, if you do a cross-section perpendicular to the y-axis, look at that. Your dy is there. There's your cross-section area. Now, that looks a lot like a square, but they haven't given us enough information to know whether it's a square or a rectangle. But whichever it is, that's what it is, either a square or a rectangle. And both of those areas we know, and you can do the area of the volume of this is going from 0 to D, or C to D, and just summing up those volumes of rectangles. The thickness is dy, and if you know what the relationship is of those rectangles, you got it knocked. This way would be pretty miserable, okay? Because you would have to know the formula, the function for this curve here, and that would be a lot harder to do. Because that's not a well-known, let's go back to these shapes they were talking about. That didn't look like a circle to me. And it was none of those others. I guess it could have been a part of a semicircle, but it's truncated. And that would be a really difficult thing to do. Same thing, whatever rectangle that is, as long as it's regular and has the same relationship going in, that's the way to do the column. Okay? And if it works out better doing the dy's and dx's, go with dy's. Okay? I think that's what they're gunning for here. So here's example 6. Okay? Find the volume of a solid shown in this figure, 725, this one right here. The base of the solid is a region bounded by the lines f of x is equal to 1 minus x over 2. Now, I don't know why they didn't do minus 1/2 x plus 1. That would be pretty obvious what that was. That has a slope of negative 1/2 looking at the xy plane, which is here, okay, and that's the slope of negative 1/2 y-intercept of 1. Okay, that makes sense there. G of x, there's your y is equal to L of x there. That's happening. G of x is minus 1 plus x over 2, which I would have written as 1/2 x minus 1. So again, looking down at it this way, the y-intercept is minus 1 and the slope is positive 1/2. Okay, going up 1 for every 2 to the right. Okay, now bounded by those two lines, the cross sections perpendicular to the axis are equilateral triangles. That's what they told us, and we can go from there. Okay, the cross sections are equilateral triangles. We know the length here, and therefore these two have to be the same length as that. Okay, so for any value x, dx that you have out here, for any value x from 0 to 2, and they give you that dimension. Yeah. Well, that's where they intersect. X equal 2. And for any point here, any x value here, at x equal 2, this is 0. At x equal 1, the length here is 0. Okay, the side of the equilateral triangle. Here it's 2, so that's going up to 2 up here too in the z plane. So all you need to know is the fact that that's the equilateral triangle from 0 to 2. And your dx is there. So what is the volume or the area of that equilateral triangle? Well, here's, not sure this, well yeah, this is going to give you the length of this as a function of x. You got your dx here, that's obvious, you got to do dx there. What is the length of this here, going from this line to this line? Well, this minus that, okay? This is the upper function, and there's the lower function. And this length here is y minus x, f minus g. So that is your base, okay, and your width is that. So this minus this minus this is going to be a 2 in there, and it will be 2 minus x, right? See that? 1 minus a minus 1 is 2, and minus x is 2, minus a minus that would be minus another that would be plus x, minus x. So 2 minus x as you go from 0 to 2. So where is a good place to do it? 2 minus x. That's the base of that. Now, what's the area of that triangle? Let's see if they show that next. Okay, yeah, this is where they get the base, length of the base. Okay? Now, what is the area? The area of that is, they jumped a little bit on you, didn't they? The area of any triangle is 1/2 the base times the height, right? And this is an equilateral triangle whose base here is 2 minus x, okay? And an equilateral triangle, this is 60 and 30, okay? So this is x minus, or 2 minus x over 2 is this length. Mine isn't drawn very well, okay? Is exactly half that. This is 2 minus x here, though you don't need that. And this will be, the ratio here is 1, 2 to the square root of 3. This is square root of 3 times 2 minus x over 2, which gives you the 2 minus the square root of 3 over 2 times 2 minus x. Okay? All right. So that's the height. Okay? H is equal to the square root of 3 over 2 times 2 minus x. That's the height. So 1/2 the base times the height would be 1/2 the base, 2 minus x, times the height, the square root of 3 over 2 times 2 minus x, okay, which would be square root of 3 over 4 times 2 minus x squared, okay, which 2 minus x was the base, and that's where they get the base squared. That's not a formula I hang on to. I don't store it somewhere in my memory base. This is how you got it, okay? So that's the area, okay? Now you've got everything you need to do your integration. This you might call, well, a dA. So the volume is equal to the integral of the area, and I'm going to pull this part out, the square root of 3 over 4, and this is going from 0 to 2, okay, going back to our original picture here, 0 to 2 on your dx's here, and then you're going to do your 2 minus x squared dx. That should be it, okay? Which is equal to the square root of 3 over 4. Now, probably the best way to do this is going to multiply it out. Later we'll get another method, but that'll be 4 minus 2x squared, 2x plus x squared, okay? Integrate that, and you get 4x minus x squared plus x cubed over 3. I'm going fast, so I'm probably missing something from 0 to 2. And we're out of time. If you follow that through, I think you see that, well, I'm doing it a different way from the book, so it'll be interesting to see if you get the same answer. Hopefully you do. This, again, will be one of those, I'll leave the rest of the student right. Okay, we talked about that in the restroom. Okay, so that's example 6. We'll pick up next. Oh, wait. Let me give you some homework exercises here. Do either 5 or 7. You can tell where they are. 7 or 11, 13 or 15, or both on any of these. 17 or 19, 21 or 23, any of the odds 25 to 31, 33 or 35, 37 or 39, any of the odds 41 to 47. We'll pick up the rest of those next time. We'll begin on example 7. All right, good deal. Sorry, I had to go back and just check and make sure I had done it right here. This is square root of 3 over 4. The class left, so that's a 4, times 8 minus 4 plus 8/3. Okay, so that'd be 4 plus 8/3. That would be 12/3 plus 8/3 is 20/3. So it would be 5 root 3 over 3. Goodness, that doesn't look like the answer they had. They get 2 root 3 over 3 out, so I did make a dumb mistake somewhere in there. Huh? That's 4. That's it. It's 4 minus 4x plus x squared. Sorry. Twice the product of the two. I was going too fast. So that would be integrating minus 4x would be 4x. That would be, yeah, 2x squared. And that would be, that one's right. So, sorry about that. All right. Evaluating that, that would be 8 minus 8, I think it is. Okay. Yeah. So this would just be the square root of 3 over 4 times 8/3. That would be a 2, so 2 root 3 over 3. Yeah, that's the answer. 2 root 3 over 3. I messed up when I did that too fast. There. All right. All right, now I'll end it. Sorry about that.